Hello everyone. Today I'm going to present to you about NNStreamer. It's a on-device AI platform which allows developers to develop their applications based on artificial intelligence and machine learning and apply stream-based paradigm to their applications. So let's get started. So here we have some popular AI-based applications and services which we use every day, starting with personal assistant like Bixby. We can now even search through photographs by writing text. Health-based applications, down to semi-automated or fully automated robots. All of these are empowered with various AI or ML-based models running in the background, performing their computations and giving us a service. So on the one hand, nowadays, we are trying to add more and more features into these applications, which makes them more convoluted and a bit more difficult to manage. But on the other hand, we want to move these applications onto our local devices. By local devices, I mean our phones, IoT devices. And all these services, we want to move these to our devices primarily because of two reasons. Firstly, our devices are now powerful enough to handle such computations. And secondly, we want to protect the privacy of our users. We want to protect their user data. So let's go through one of these examples in detail and understand how this is all happening. So here we have a simplified model of personal assistant based on voice. So on the bottom left, you will see a microphone through which we can receive an audio input query. It is converted to a text or intermediary format before being passed to the domain classifier. The domain classifier can classify this query based on the content. So for example, if a user asks a simple question, then it will be classified to the question answering module. We have 5 core modules here represented. It will be classified to the question answering module, and if it is a private query, then it will first be routed to question answering and then forwarded to information retrieval. So based on the content, after the query has been classified, it is routed through these core modules. And these core modules, they're not just single blocks. They in themselves are actually more blocks being interconnected. And this overall units form an interconnected web of various AI or machine learning based, or even just simple vision based blocks, computation hungry blocks. After these modules have processed their inputs, the answer retrieval module will take in the outputs from all of these modules, adapt it based on the environment and the device which we are using, convert it to audio format so that it can be given out to the speaker, in this case. But a virtual personal assistant should be able to do slightly more than this. So we will add a camera as an input. That's a pretty common one. We should also be able to control other devices. We should be able to get some more information from other devices, not just the device which we are operating on. So this one represents here a personal assistant model. In this case here, if you want to deploy this, or if you want to run this onto a device, partially or completely, we will usually go through 2 steps. The first step would be, we would be going through a research, trying to find out the best model, get us the best accuracy and performance. And the second step would be to deploy those applications, to deploy those models. We will quantize those models, do whatever optimizations we can do, and get the best performance onto our device without losing our accuracy. However, those 2 steps are not enough. We need to look at all of these models connected. We need to be able to connect them in a pipeline. This can be a very complex pipeline, or it can be even a simpler one. Connect these models together, handle the data movement, synchronization, the management of the pipeline, so as to get the performance of all of these models when they're running together without having the overhead of that management. That is a very important factor in getting the performance out of our service. And to get this kind of performance in our service, this is exactly why we have made NNStreamer, so that developers can take in their machine learning models and deploy them with our NNStreamer application. No matter how complex or simple their application is, they can get the best performance without a high cost of development. So let's look at how this example would be deployed with NNStreamer. It's pretty much simple. We'll do 2 steps. The first step would be, we have provided various elements with NNStreamer. We go with the pre-processing or post-processing elements. We choose those elements. And with those, they can be encoder or decoder in this scenario based on the audio, and we connect those elements. The second step, we take in the original abstracted thought process which we had about connecting various core units, domain classifier, adaptation modules, connect all of these things together, and done. If you want to interface with the hardware, in this case, you want to interface with input-output, like you have microphone and speakers, you can have camera modules, all of those wrappers are provided with NNStreamer. You have made your model, the core models, you have used PyTorch or TensorFlow. You might have used various frameworks to make them. We can all support them. You have used different backends from CPU, GPU, maybe your own data signal, your own DSP. We can support them as well. So if you have made your model and you want to run them with your application, we recommend you to use NNStreamer. However, this is a very conceptual example. So let's go into a real working example. So here we have a small demo of hand and face detection being running. And this is running on Android with TensorFlow Lite as backend. This is a simple example. If you want to get a more hands-on experience, we have application on Play Store called NNStreamer Multi. You can install that application, or you can use this QR code to go to that installation page. The application has 4 models inside it: hand detection, face detection, pose detection, and a generic object detection. You can use one or maybe all of them together, make a pipeline, and get the feeling of how the pipeline is being made. So in this example, let's walk through this example and make this example ourselves. And after giving this working example details, we'll go through our details about NNStreamer and which platforms we support and all such details. So here is the pipeline, the actual pipeline which was used in making that application. At the bottom, we have our source and sink elements. The source elements and the sink elements are using the wrappers provided with NNStreamer, and those wrappers interface the complete pipeline with our inputs and outputs. The captured video from the camera is pre-processed firstly, in this scenario flipped and cropped before being scaled. We have 2 color schemes used here for the elements. So the blue color elements represents data in the video format. So they can be your frames in RGB or NV12 encoded formats. However, the orange color elements represents data in tensor format. So in tensor format, you can represent any arbitrary data in a multi-dimensional array. So here we have, after applying scale to our video, we convert it into a tensor format, we normalize the data, we do object detection, we run the object detection, which was the core part, what we wanted to do. We decode the tensor. Decoding the tensor means that the object detection by itself will give us coordinates of the bounding boxes, which we saw in the previous slide. Those coordinates needs to be converted and drawn as a box. The decode tensor will draw the box for you. Once decoded, we now have the data in the video format with the boxes drawn. The original video, the pre-processed video, and the decoded video is then passed to the video mixer. The video mixer overlaps them together and gives it out to the video sink, where it can be rendered directly. All of these elements which we have used here and many more are provided with NNStreamer. You can just plug them in as per your use. If you want to have multiple object detection running, you can connect them in parallel and run them. So this working application, now I want to ask all of you a question. If you people are interested, we can walk through the code of how to write this application. I assure you that this whole pipeline can be written in just 5 lines. And I'm not kidding you. I also like the 80-character rule, and so I won't make those lines very long. So by show of hands, if significant number of people are interested, we can walk through the code, or we can skip them towards the end. So there are some people who are interested in the code, so let's go through the code. So we will have split the whole pipeline into 5 parts. Each part we will write with a single line of code. There are 2 lines, 1 line is a comment, so we'll ignore that. The second line counts as the code. And while making the pipeline, there's the exclamation character used. The exclamation character is a connector which connects the 2 elements so as to make the pipeline, or you can say a graph. So here we have the H2 source, which is the camera source, which connects to a crop and flip, gets us the pre-processed video. That same video is then passed to the scaler, which scales it, tensor converter converts to tensor, and then transform, which normalizes the data. Tensor transform is a generic unit which transforms the data, and you can use various functions. So you can transpose, you can normalize, you can add, subtract, generic function. Then we run our object detection model. We provide in our file, which we are running, and tensor decoder, which decodes it to the video. The video mixer then takes that decoded video and gives the output at the video sync. So that gives us the final video, and the last connection which we form between the pre-processed video and the video mixer. So if you combine all of this code together, these 5 lines, we get our complete code. These are 10 lines. The 5 lines are comments. You can ignore those. So in all of this 5 lines, we have made the complete pipeline to run the object detection on your phones. This pipeline, if passed to NNStreamer, this pipeline will connect your camera to the object detection file which you have provided and get you the final video which you can take in and render in a window of your application. If you want to run this pipeline, if you want to take this pipeline, compile it and run it now, I recommend that you make a small changes, like video crop. Please specify the size to which you want to crop, or if you're specifying the file, specify the full path, and this pipeline will work in your application. So now that we know some scenarios where we have used NNStreamer and why we need the NNStreamer, let's go into details about NNStreamer and where all we can find NNStreamer. So the remaining of the presentation, I'm going to go through with what is NNStreamer, where all NNStreamer is present, some details about NNStreamer, and finally conclude with some takeaway points. So let's start with what and where is NNStreamer. So NNStreamer, as we know by now, it's an on-device AI framework to deploy ML-based applications. If you have complex or simple ML models interacting with each other, the NNStreamer is for you to deploy those applications. We are an open source project hosted on GitHub. We have LGPL license. NNStreamer at its core is an extension of GStreamer. If you're not familiar with GStreamer, GStreamer is an open source framework for making graphs of media handling components. So GStreamer allows us to connect various inputs and output sources and handle the data in video, audio, text formats. It can allow processing in those formats. So the way NNStreamer extends GStreamer is by adding tensor type to it. So by adding tensor type, we can support any form of data. And once we support any form of data, then supporting ML-based models is pretty simple. So we provide various plugins which allows us to process those data, and in those plugins, we support various frameworks. Those frameworks allows us to process our data, run object detection or any model. When I say ML-based model, they can be your convolution networks, RNNs, LSTMs, but they can be even your decision trees, Bayesian models, any models which are supported by a framework, we are supporting them. NNStreamer is available on multiple platforms. On Tizen 5.5, since Tizen 5.5, NNStreamer comes in pre-installed. With Android, you can download our NNStreamer package from JCenter and import it in your application. With Ubuntu and macOS, you can install it with our PPA or Brute app. With Yocto, you can include it as a layer in your build and get it ready. So this means that if you're writing an application with Tizen or Android, you can import our package via Tizen Studio or Android Studio directly and package it with your application. But if you want to write an application with these OS, you want to know where our package is inside the operating system. So inside Tizen, GStreamer comes inside Tizen as packaged inside the middleware OS. So we have made NNStreamer also available inside the middleware OS, along with the NNStreamer C and C# APIs. So the application developer can directly use this APIs in their applications. However, inside Android, the scene is slightly different. Android doesn't provide GStreamer inside the OS pre-installed. So we have packaged GStreamer along with NNStreamer in our package along with Java API. So you can get this package from JCenter, include it in your application, and package them together when ship it. And in this way, you can use NNStreamer in Android as well. So now we know how to write a pipeline. We know how to use this with NNStreamer, but we don't know how to interface with NNStreamer. Once we have created the pipeline, how do we pass it to NNStreamer? So this is what we'll talk about next. How and when can we use NNStreamer? And this is where the APIs of NNStreamer, which I talked about, will come in. So we have C and C# APIs for Tizen. We have Java API for Android and C API for Ubuntu. The API set is powerful but very simple. The first set is creating the pipeline. We already saw how to create the pipeline. We create our own pipeline. The second step is we want to register those models which we are using in the pipeline and register those pipelines with the API. The third step is we want to run the pipeline. The running the pipeline, in the example which we used, we connected it with a live camera source. So in that case, the live camera source is going to be providing the data and drive the pipeline. We don't need to load the input in that case. But if we are using an offline data, then we want to load the input with every run while we are running the pipeline. Once we are done, we can destroy the pipeline and close the application. It's a simple API, but allows us to handle simple and complex, whatever scenarios of networks you're connecting. Apart from this API, we also provide a more detailed API where you can handle each element. You can get a handle for each of the elements in the pipeline. You can access what data they are processing, how the data is being flowed. You can manipulate the pipeline and do a lot of things. This is the pipeline provided by, this is the API provided by NNStreamer. However, there is an extra set of API provided by GStreamer, which you can also use, as NNStreamer is an extension of GStreamer. The GStreamer pipelines allows you to access each element in more depth. So inside NNStreamer, each element is class-based, handling the inheritance. So if you want to access some data inside the deeper level of the class, you can do that with GStreamer API. Or you can club some elements together and handle them together at a more abstract level, making the pipeline more simplified yet abstract. So all those things can be done with GStreamer API. We support various backends with NNStreamer. CPU, GPU, of course, are supported. We support DSPs. Samsung NPU will be supported by the end of this year. If you have your framework and you have your own backend supported with that framework, then we can support your own backend as well. If you have a proprietary backend, yes, we can support it. If you have your own custom layers, like this is a very common use case that people write their own layers inside the framework. They have a specialized layer doing their operation, and they want to support those layers with the platform, then that is also supported. You directly bring in your compiled binary of the framework, and you link it with an NNStreamer. And that custom layers or your backend is also supported then. The supported frameworks which we have are TensorFlow, TensorFlow Lite, PyTorch, Caffe2, Movidius NCSDK. We also support Tizen NNFW framework, which allows us to accept various kinds of backends. NNFW supports CPU, GPU, Neon backends. We also support binary formats of models, which is just, binary format is just simply you take in your model which has particular interface provided, and it is just compiled as a shared object, and we can support that as well. So now knowing that we can, how to use NNStreamer, where to use NNStreamer, what is NNStreamer, we'll go into why one should choose NNStreamer. What benefits do they get when they choose NNStreamer in writing their applications? So NNStreamer was written to give you the best performance. With NNStreamer, we have targeted that the time to market reduces a lot. We have focused on low cost of development for our developers who are trying to use this platform. And we'll consider these 4 reasons out of many why one would use NNStreamer. So we'll discuss each one of them in slightly more detail. So the first reason is efficiency. We have tried to reduce the overhead of our framework, focus on minimizing the latency which we'll get, especially in live stream data, in our live stream data pipelines. The latency matters a lot because our data is coming in live. So we have focused on those kind of issues so that the latency is minimized when using the platform. We provide yet another API which allows you to use NNStreamer for very simplified situations. In those, the overhead of a complex pipeline that has been minimized, even though it's just a few milliseconds, but even that has been removed so that the developers get their best performance. We have adapted it for high bandwidth applications with our low cost memory handling. We have benchmarked our application with a fault detection mechanism. This is the pipeline. This is even an abstracted pipeline. This is not a complete pipeline, which was used in the application. There were 18 CNN computations running per output for this example. So if we look at this pipeline, we have 2 sensors. We have a data vision sensor, DVS, and ultra wideband sensor on the left, which are our input sources. The data from them is pre-processed, converted into tensor format, and we have aggregators, muxes, a lot of things going on in this pipeline. And there are 3 particular elements which are our models. We have 2 TensorFilter custom. These are the binary formats of TensorFilter, which I talked about earlier. And there is a TensorFlow Lite-based model being used here. We take in all these inputs. Some models are taking in the inputs from the other models. And finally, the output goes into the sink, where it can be extracted out. This particular pipeline was written by a developer in less than 2 days. He was able to learn about NNStreamer, write this pipeline, debug it, and get it deployed in less than 2 days. And this was compared against a control program written in Python, which took him over 2 to 3 weeks to write, and still not able to get the best matching performance. So the low cost of development and the reduced time to market is very important for us. So if we compare the results, the statistics of this particular example of fault detection mechanism, The CPU usage is pretty much maintained. However, the memory impact has been reduced to half. And the throughput, the frames per second as the output, they have increased by over 50%. So from 20 frames per second to 30 frames per second. And the amount of code to be written, that is also reduced by 1/3, where we are comparing Python code to C code. So that's a big difference. And this was tested on RTX 530. Yeah. Secondly, ease of use. As I've already emphasized on the short time to market, we are trying to reduce the amount of workload for a developer. Once his models are ready, he should be able to market it very fast. And the abstract APIs allows the developers to take their complex structures and make them more managed. They don't have to arrange them. They don't have to worry a lot about managing all the structures. NNStreamer will manage their pipelines and get it done for them. Thirdly, the modular structure of the pipelines allows you to modify the pipelines and use various elements which are provided as per needed. We have an infilter which forms wrappers, allowing us to use various frameworks. The supported frameworks list, as we already discussed. There are converter elements provided which allows us to convert between various media formats. So you can convert from video, audio, text, back to tensor format and back and forth. Utility elements, there are mux or demuxes, aggregate, allowing us to create complex topology of pipelines. Or we can have simplified ones as well. There are transformer elements to manipulate data before being passed to the models, simple manipulations, transpose, normalize, you can change the dimensions, all such things. And we have connectors. The connectors play a major role if we want to interface our pipeline with outside elements. If we have sensors in our phone, we have microphone and camera, and you want to interface those with the pipeline, you can use these connectors directly. You don't have to worry about what is the interface of those inputs. These wrappers will directly allow you to connect them with NNStreamer pipelines. You have Robot OS. You can subscribe to the data of Robot OS directly with your pipeline. We also have a repo connector. This allows you to run RNN or LSTM-based models and create such a recursive loop in the pipeline. So you can create a loop-based pipeline as well. And lastly, the fourth point is, here we'll discuss two of the optimizations which run in the background while the pipeline is running. So this is an example of automatic synchronization. This is a subset of the personal assistant, which we saw a few slides earlier. We have 3 models running in together and giving us the output. The 4th module, which is answer retrieval, takes in the output of those 3 modules together and finally gives the output. As we notice here, models are running on different frameworks, so it is supported that you can have different models with different frameworks in the same pipeline. Now in this scenario, model 1 runs at 30 frames per second throughput, but model 2 and model 3 are running at different throughputs. So in this case, answer retrieval module, we can specify what throughput do we require here. And NNStreamer, in that case, will automatically do the synchronization of the outputs of these models. It will drop some of the frames. It will drop exactly 1 and 2 frames for model 2 and make its output at 30 FPS. Correspondingly, reuse the frames for model 3 so that all the outputs of these models are synchronized and can be used by the answer retrieval module. However, there is one problem in this. If we look at the model 2, we are dropping the frame after it has been processed. So we are wasting our resources. Second problem is all the elements in the pipeline before these models will be running at 60 frames per second because model 2 is running at 60 frames per second. They have to support this model. So in that case, NNStreamer also performs controlling of the data stream rate. So in this case, it will limit. In that case, instead of dropping the frame after being processed, it will top the frame before model 2 has been processed. Hence, model 2 will run at 30 FPS. And correspondingly, this dropping of frames will be backpropagated to each of the element. And in that case, and finally, all the elements in the pipeline will be limited to 30 FPS, just because we set the final answer retrieval module to 30 FPS. So this not only saves us the computation power, but if we have such pipelines on our phone, which are battery operated, they save us a lot of energy and battery time. So lastly, I will conclude with a few takeaway points. So if you have an application which requires complex or simple structures of a pipeline, you have different kind of backends you want to support. You want to run your application on various platforms. We recommend you to use NNStreamer. All we require is that you bring us your models, and we'll wrap them around in our pipelines, manage everything for you, and ready to be used in your application. We are focusing on real-time data stream, but if you have offline data, that works as well. And before I end this is our GitHub page. You can go to our GitHub page. You can, if you have any questions, if you have any concerns, you can ask me. You can raise an issue there. And if you want to contribute, request more features, you can go there, and if you like the work, you can star us. And lastly, you can rate, you can fill in the evaluation with SDC app. So if you have any questions, any concerns, yeah, please do share. Yes.
So I was playing.
Sir, can you use the mic? Yeah. Yes.
As I was listening to you, it seemed like a very powerful concept, and especially because you're doing it on mobile devices. So I was playing with the NNStreamer multi-model in single, then I downloaded from the Play Store.
Yes.
And I discovered some very different anomalies and glitches, kinds of things.
Okay.
So the one thing I noticed was in the multi-model, if I did both the face and the hand, and then removed the face, then it started to recognize my face as a hand. Whereas if I had both of them on, then the face and the hand were recognized separately. So I was curious whether it's because the Android and Java and whether the remnants in memory or the models were remaining, that was playing into all this, or because the models are the same. And I also noticed that the multi-model NNStreamer had much better performance in detecting things, even object detection, compared to the single detection. So for example, it detected this chair as a fridge, whereas the multi-model actually detected it as a chair. And the face detection didn't work at this long distance at all, worked with me in the back end. So some issues, maybe with the models, but I was curious how the NNStreamer was playing into producing some of these artifacts.
So in this case, NNStreamer is just going to take in the models and run the models. NNStreamer will support multiple objects being detected at once, or even a single object. I think, well, thank you for reporting us a bug about when switching between models, it has some bug, and we will try to fix that. Regarding the faces, like the far faces not being able to detect, or NNStreamer multi detecting more objects than NNStreamer single, I think the models being used in both the applications are slightly different. So it's the difference between the performance of the model and independent of the platform which is being used. So we use off-the-shelf models. We didn't develop those models by ourselves. So we will maybe update the models, and hopefully we'll get better results with that. Does that answer the question? Yeah, okay. So if no more questions, thank you, and I hope you enjoyed the talk.